Okay, so let's get going. Welcome to this week's colloquium at the School of Astrophysics. We are glad to have Dr. Manajit from the National Renewable Energy Laboratory at in the US. Dr. Sengupta, like many other speakers, did his undergrad at the Sengupta College in the physics department, and then after taking a short break, he went to do his PhD in meteorology in at Pennsylvania State University. He has held research positions subsequently at Pacific Northwest National Laboratory, Colorado State University. And finally, he joined, in 2009, he joined the National Renewable Energy Laboratory, where he has been ever since. Dr. Sengupta's research interests have been cosmic modeling, assimilation and observation analysis, as well as remote sensing, forecasting, and analysis of clouds and solar radiation. At NREL, he leads research in the areas of solar measurement, modeling, resource assessment, solar forecasting. Dr. Sengupta was a member of the GOZAR science team responsible for creating products for the next generation of NOAA's operational weather satellite. He's also led research as part of DOE's climate change program to study the impact of clouds and surface radiation. So Dr. Sengupta is one of our alumni. He was in the 85 to 88, 89 batches, and we have kids of his classmates among the audience. And also he knows about the solar radiation all over. So he has worked on solar radiation in India as well. So if you are feeling cold this winter, you can ask him about where to go to get the most sun. Anyway, so with all that, let's welcome Dr. Sengupta.
So let's get going. So I move this. So tell me if you can't hear me, then immediately tell me, because sometimes I tend to go a little soft. Anyway, so what I'm going to do today is talk about ultimately what I'm on the bottom. It doesn't move forward. It doesn't move forward. It doesn't move. Okay. So what I'm going to talk about is our work, a very practical application I was discussing with some of you, essentially solar radiation for solar applications, essentially photovoltaic applications. I'm going to talk about all those applications, but it'll be pretty overview of a lot of things, but I will definitely give you an introduction to what the basics of what of all the physics we are using. So let's get going. Is this better? Okay, that's what I said. Tell me if you can't hear me. Tell me. So objectives of our research. I'll quickly go through it. Is ultimately the overall goal is to decarbonize the electric grid using renewable technologies, and we're trying to do that to combat climate change. One way of achieving that is deploying large amounts of solar and wind on the grid, so it displaces all your coal plants and other plants, which are fossil fuel-based plants. Again, this is only possible, it's a market. So this is only possible when the costs of these technologies achieve grid parity. Grid parity means per kilowatt hour or whatever unit, the price should be lower than, say, a coal generating facility or a nuclear facility or whatever you call it. Otherwise, the market will not accept it. So that's a big important thing. Is we're already there practically on solar, so it's just expanding. But anyway, we want to reduce the cost of deployment and operation, so that's why we conduct our research. This is just a snapshot of how solar has grown. It's exponential. So on the top two panels, essentially, it's the cost. of photovoltaic systems and energy storage. So as you can see, the costs are going down exponentially. And the growth in solar is on the bottom right there. That's the growth of solar. It's an IEA report, and as you can see, that look at the trends.
What is the latest number in the section?
This is this one.
Yeah.
This is 2022.
And what is the first one?
This is what?
2030. So it's like each year.
Yes, it's an annual thing. It's what is the annual growth, and as in that pie chart,
Only in the last 10 years, it has increased that.
yes. Before that, solar was not as mainstream. You need policies. There's a lot of pushback. Unless you have the government behind it, it doesn't happen. And the costs were much higher. So you can see what the costs were and where it is now. This is the cost curve. So that's why this is happening. And this year, there's 236 gigawatts of solar being deployed. So total is 1183. And next year, it's probably 1.5 times that. So that's what solar is taking over the world. And I'm happy about that. This is global, of course. So this, if you go to this IEA report I have referred to here, you probably have access to the presentations. These reports are very illuminating on and gives a lot of details on how things are happening. So I will probably have some of the references here, but if you need more references, I can definitely point you there. These reports are free. The IEA reports and all of it is just publicly available. So the next question is, why do we need solar resource information? We're putting out solar. So why? So again, when you build a solar plant, there's these stages of a solar plant. There's a pre-feasibility stage. They try to understand where you want to locate solar generally. Then you locate a piece of land. You do a feasibility study. Then once you've done the feasibility study and say, okay, this might be beneficial, then you look for financiers and you do due diligence and acceptance. And then finally, if you deploy your plant, you do your operations and maintenance. So at all of these stages, you need an understanding of solar radiation. How much solar radiation is there in the long term? So what is it going to produce for the next 20 years? Now they're trying to build PV panels which will last 50 years. So they want to know what is the trends in solar radiation? Will my plant still be viable after 10, 15, 20 years? And so solar radiation is an essential, it's again, one thing to remember is sunlight does not have a market rate. It's variable, but it's free. It's something we just try to harness the best we can and improve on the technology. So we just use the sun for all our energy needs. So that's why that's where all the stages of a plant development, and they end up using our solar measurements or solar models. What are the challenges, current challenges? These are the current challenges. I'll talk about other stuff, but these are, so like I mentioned, there's higher levels of deployment, a lot of solar, so now it's variable. How do you integrate it into the grid? You don't want your lights to go off or flicker because the clouds came over the sun. So, and if you have say 50% solar and suddenly there's a drop in generation, how do you handle that? So that's a big question. New technologies are coming online. There's this bifacial technology I'm talking about. Solar panels can receive radiation and generate from both sides of the panel. There's these things called tandem cells, again, which are like multi-layer cells. They require new types of data, such as spectral data, high-resolution albedo data, because you're using the sunlight reflected from the surface. There's also this issue of solar being deployed in more diverse environments. It's being deployed all over the world. So there is always this need of different types of data. In the Middle East, they need aerosols, very high accuracy aerosol information, because there's quite a bit of aerosols out there. Again, solar becoming a key focus, there's also this issue of your panels getting dirty. If your panels get dirty, you produce less. There's huge degradation. So there's necessary, people need information about soiling, humidity, ultraviolet radiation, because panels degrade. So they want to understand how panels degrade. And also finally, as the climate changes, so does the need to predict energy needs and performance for the future. So there are all these challenges which we're working on as right now. So let me quickly jump into some very basic solar radiation concepts and go pretty quickly, I guess. You probably know what the extraterrestrial spectrum is. This is the spectrum of the sun above our Earth's atmosphere. Well, there's, of course, as you can see, the smooth curve, which is the black body at 5,800 kelvins. That's your black body. It's a smooth function. And then there is the actual extraterrestrial spectrum, which is part of a standard. We normally, because we work on with industry and there's money riding on things, you will see I talk about a lot of ASTM, is American Society for Testing of Materials. There's ISO, International Standards Organization. There's IC. All of these, they build standards which industry follows. It's a good thing when you follow standards, is because everybody has some equivalency. Instead of doing ad hoc things, you do the same thing. But nevertheless, that is you have the extraterrestrial spectrum, and you can see there's the UV and visible where the peak is, and then there's the rest of the infrared. And then generally what we do is we try to get to a solar constant, where the solar constant is like 1361 watts per meter square on average. But if you look at it, the total solar radiation, it varies slightly, like a couple of watts per meter square. The interesting part is that solar spectrum, the solar constant used to be 1367, and now it has changed. So science is, as we get better measurements in outer space, we again correct this, and that again this. So essentially, what I'm saying is we use the solar constant all the time, and then when we calculate the extraterrestrial radiation at a certain time of the year at a certain location, you adjust it for the distance of the Earth and Sun, because as you know, it's an elliptical orbit, so the distance varies at different times of year. So ultimately, we use this thing called ETR, the extraterrestrial radiation, which is the solar constant adjusted by the Earth-Sun distance, where R0 is, as you can see, is the average Earth-Sun distance, and R is the actual distance. But anyway, so this is what we will use. Now let's look at the basic definition. I'll use this throughout the talk. On the left-hand side, this shows basically, let me see. This shows you what's happening to the sunlight. There's all this scattering and absorption which happens in the atmosphere. So a photon coming in from the sun into our Earth's atmosphere what could happen? It could be scattered, could be absorbed, or it could just come straight through to the Earth's surface. These are three possibilities. Essentially, our work is to understand how these photons interact with the clouds, aerosols, and the gases. And then ultimately what we want to do is we want to get to these three quantities: this direct normal irradiance, this DNI. I'll be using these terms very frequently. DNI is just what comes in and hits the Earth's surface in a narrow beam. It's like if you use a measurement, it's a 5-degree field of view. That's how we measure it. So whatever is coming in through this 5-degree field of view, we call it the direct normal irradiance, or DNI. Then there's the diffuse. It's everything else, coming from everywhere else because of the scattering and ultimately reaching the Earth. That's what is the diffuse horizontal. So there's the direct and the diffuse. And ultimately, if you look at it direct normal, so this is a normal plane, this is not the horizontal plane, but that's why you have this cosine correction. And then there's this GHI, or global, which is everything. So this is a fundamental equation. So if you have measurements of any two, you can calculate the third. But normally what we do is we measure all three for redundancy so that we know that our measurements are good. But nevertheless, GHI, DNI, and DHI is what I'm going to use. Then the complexity of our problem is that if you really look at it, that was horizontal. And then this is a PV panel, say, and what we end up having is we have to have information about what's coming from the ground, what's coming to the backside, and plus all this other information. All of this gets combined for usage in modeling a PV plant. Nevertheless, let's get into some more. Now that's basically the very basic things which you need to know before we go into what we're really doing. So let's see, how do we model or measure solar radiation? We could use ground measurements, and each has its pros and cons. So if you look at ground measurements, you see there are these instruments: pyranometers, pyrheliometers. Pyranometers are measuring the global radiation, the diffuse radiation. Pyrheliometers are pointing at the sun, measuring that 5-degree field of view. There's some advantages, of course. There's accurate and very high temporal radiation measurements. You could get 1 minute measurements, practically measuring every 1 second or 5 seconds, and so you could get very high resolution in time. Disadvantages are it's very local coverage. It's regular maintenance. At NREL, in our case, we clean it every day. We check every instrument every day. It's time consuming, and expensive. So and it's local. So use one point in the ground means just that local place. Then there's a satellite derived, there's big advantages. There are, again, multiple types of satellite models. There are empirical models, there are physical models. I won't go into details right now, but nevertheless, there's a big advantage. You can cover the whole globe. But there's some disadvantages to that. It's complicated retrieval process. So of course, the uncertainty is a little higher. And then finally, there's these weather models. Most of you see the prediction for weather. There are these physical models which predict the weather. Again, those models can give you this solar radiation, but they are probably the most uncertain because these weather models, the weakest point for them is clouds and radiation. Clouds, they can't predict clouds very accurately most of the time. They underpredict. So this is probably a good, an easy source, but a very uncertain source. So let's get into solar resource measurements. So what do we do in measurements? Here's, like I said, we have these pyrheliometers. So this is just your pyrheliometer pointing at the sun. This is a solar tracker. So this is these solar trackers are 2-axis. So they always ensure that this instrument keeps pointing at the sun all day. These are diffuse measurements. So this solar tracker is controlling the shade balls and you shading the direct sun, so you can measure the diffuse. And these are global, so they're not shaded, and they essentially measure the global. So these are very simple setup. The devil's in the details of how good is the equipment. Again, you could buy the fanciest equipment and not maintain it, and you get very bad results. You have to calibrate it regularly. So there is this issue of, okay, this is the system, but there's more work to be done essentially to get good measurements.
But the diffuse measurement one, I mean, the instrument has to be pointed at different directions and.
No. If you go back, let's go back. It's like, it's just this thing was just, the sun is shaded. So this ball moves, this ball is attached to the tracker. Okay.
So light from photons from all directions can come.
Except
the sun's direction.
Yes. So that's the diffuse. And so is the 5-degree field of view, everything else except that 5-degree field of view. That's diffuse. So again, like I said, it's the most accurate source of data. If instruments are of high quality, first thing, then they're regularly calibrated. Calibration is a big issue. A lot of you do modeling, and if you get some observations, you think that observations are perfect. Or I used to do that when I was in the beginning of my career. Well, I got these observations, great measurements, perfect. The observations should always be checked and their uncertainty assessed. And basically, otherwise, your results could go all wrong. So it's just in every field, I think it's essentially, then there's this issue of quality controlling the measurement and quality assessing. Quality assessment is one thing where you assess the data after the fact. You can't do much about it. You can't correct it. And quality control is when the measurement is being taken, you ensure that good measurements are being taken. Again, these are expensive, but again, if you can do all of it, you'll get very good measurements, which are of very high use, like value. So the other thing I wanted to mention here, and I won't dwell too much on it, is this thing called traceability. Ultimately, every measurement traces to a standard. And in the case of solar radiation measurement, it traces to this thing called the World Radiation Reference. These are 5-6 instruments sitting in Davos, Switzerland. And everybody takes their primary reference to Switzerland every 5 years. And they intercompare and get a calibration back. They bring it to their home country and then use that as a reference to propagate the calibration to other instruments. So this is the chain of things. And as you can see, the World Radiation Reference has a 0.3% uncertainty. As you start to transfer it down the chain, ultimately to field deployments, you end up with ±3 to 5% uncertainty. Even for your best measurements, you clean every day, you do whatever, you buy the most expensive instrument, but ultimately you will end up with an uncertainty in your measurement. So as an example, if it's 1,000 watts per meter square is your measurement, what is your uncertainty? That's significant. It's like 3% is 30 watts per meter square, plus minus 30 to 40 watts per meter square. So that's significant. That's your uncertainty. You can't go beyond that point. But nevertheless, there are standards which help you get to the best measurement possible. So again, I mentioned this.
But that 3% sounds too high in the sense that when you measure the brightness of a star, for example.
Yes.
Nowadays, photometric accuracy is much better than that. Why is this so high, this 3%? Measurements are.
No, your measurement is probably, but it's your measurement are probably, your precision is very high. But your uncertainty in the measurement by itself is that range. It's not necessary that every measurement you take has a 3% inaccuracy. It's just that you cannot say that my measurement is like half or perfect, or so you still have to have this little band which says that even though your precision of your instruments might be, we could
systematic.
Yes.
Yeah.
No, the systematic is biased. This is like random. Some of it is random, some of it is systematic. Pardon?
Is there any position?
No, oh, okay. This is historical. It's not a standard. It's essentially this is what it is. It's watts per meter square is an operational standard, and even though they have the 6 instruments, 2 of them belong to us at NREL. We gave it to them on long-term loan. So there were very few labs originally, and this was set up by WMO, the World Meteorological Organization.
Better if it was some tropical region instead of some.
So no, this is just a standard setup, and then you essentially, this is the top of the chain where everybody takes their instrument, and this is a world standard. They call it the world standard group. This is the world's like meter. You have this meter. It's kind of similar, and then everybody has a similar type of instrument. India owns few. Everybody, so they take it there every 5 years and bring the thing back. So it's just a historical thing. It could be at NREL. So what happens is every other year, like 5 years at IPC, International Comparison in Davos, but the other 4-year IPC comes to NREL because there is a requirement from ISO that there should be inter-comparisons held every year to maintain ISO accreditation. So every September, if you can come to NREL, and if you have these cavity radiometers, there's people from probably 30 countries who are sitting out there on the deck staring at the sun. Okay. So this here's an example of a solar radiation measurement, just a couple of days from NREL. I pointed out here's the website. And you could get data from 1981 to today at probably with a 1-minute lag. This data comes in, so you can get a lot of data. If you wanted to, what does solar radiation look like? If this piques your interest, you could go there, and there's massive amounts of data, very easy to get. Just an example here, because this is, remember I mentioned GHI, DNI, and diffuse, DHI. So this is the global. This is GHI. This is diffuse, and this is your DNI, and this is a clear day. This is a nice clear day, blue skies, very little aerosols. This is what happens. Here's, okay, the blue is diffuse, DHI, diffuse radiation, everything except the sun. A direct sun, everything except direct sun, and diffuse is very low because it's clear sky.
So red is looking at the sun, blue is not looking at the sun, and green is the sun. But then what is the source?
No.
Yes, scattered.
Source is really scattered.
Like you look at the day sky, and it's still bright.
Yes, why is your sky blue? That's the answer. Your sky is blue because all that photons ultimately, so and really scattering, most of the shorter wavelengths get preferential scattering. Green, yes, green. No. Green is looking at the sun. No. Green is looking at, now here's the confusing part. This is larger, but remember, this is normal incidence. That's why this is larger.
That's why the sun is.
So if you multiply it by the cosine of the zenith angle, which is the angle between the vertical and the actual sun, yes, and this is the global. So now, if you look here in this one, the direct is the green. Remember, I said the direct is the green. So the direct goes to zero because here's a cloud. There is no direct radiation. The cloud is obscuring everything. So it's all zero. Here's the green. So then what happens is the diffuse becomes equal to the global because there is no direct sunlight. These are the trickiest because you can see the clouds coming in and out, in and out. So now look at what is happening to the direct. It drops down to practically zero, goes back up as if the sky is clear. And this is what we are trying to understand and essentially predict and give information on solar plants. The only advantage of the solar plants is this is a point on the ground. A solar plant is a big area, so there's some averaging going on. So it doesn't look so disastrous. That's the only advantage. It's October 27, 2023. I just pulled two examples. I just wanted to pull. I just wanted two representative days. Yes. Yes. So yes, if you go there right now, you will get data continuously. But there is more measurements, not just solar radiation. There's a lot of solar instruments you can do. Essentially, this is a setup for evaluation of models, even development of models. So we have a lot of measurements just for that. Then like I mentioned, we have to data quality. We have to assess our models. So we have the software, which is called Syracuse. SERI is Solar Energy Research Institute. Before NREL became NREL, it was a little thing which got started by Jimmy Carter a long time ago, and then it became a national lab. But they developed a software called SERI Quality Control. Essentially, what it does is, again, using the same concept, KT. So look at KT, it's just a normalized value of the GHI. So it's global divided by the extraterrestrial radiation multiplied by the zenith angle. And so ultimately, so we normalize these. So KT is for global, KN is for direct, and KD is for diffuse. And KT is equal to KN plus KD. Ultimately, we are normalizing it, but this is a closure equation. This is, and what we try to do is, because we have these three components, we try to see, the software essentially checks to see what the discrepancy is. So there is a limit beyond which the software will tell you, it flag the data and say it's bad. So there is all these, this is an automated software. You could essentially flag your data as good or bad. Here's an example of what we produce out of that software. If you really look at it, on the left is all these different, there are 99 flags. So there's a lot of information in these three components of data. So if you look at this blue plot here, it's the vertical axis is the days in the month of September. This is September 2023. And this is the days, and this is the full day during that month, like morning to afternoon. It's like sunrise to sunset. And here is the plot for the KT, KN, and KD. Ultimately, these flags and provides us an assessment of the information. So we ultimately get a summary statistics table. Our goal is to have 95% plus data has to be high quality. That's our milestone for our funding. We have to ensure that 95% of the data is good. So if there is a snowstorm, we have to clean it very quickly. Any weather events we have to take care of. Nevertheless, that's what it takes to get a good data set. And here's the software which we use to flag our data. Then what we want to do is we determine the uncertainty. Remember, I mentioned there's a 3% uncertainty or whatever. So what we have to do is we have this data quality assessment. Bad data, you don't assess uncertainty. Bad data is bad data. Then you take the good data. We know what the pre-measurement uncertainty, what is the uncertainty inherent in an instrument. The instrument, based on instrument quality, on the calibration, we kind of know that, and that's a fixed number. And so what we do is we use this information to ultimately assign a certain uncertainty to every measurement. This is ongoing work right now. So remember, I mentioned that the instrument has its inherent uncertainty. And I showed you that how the uncertainty grows. So this calibration, the spectral response, the zenith angle, the data loggers. Data loggers have some noise, non-linearity, aging, all of this gives this band of uncertainty for the instrument. And then we use, here's the chain, how we assess the measurement uncertainty. And I'll go through it very quickly because I think we need to, I don't know how much time we have. I don't want to, I will be very cognizant of everybody's time. We have 20 minutes, so I'll speed up a little bit on this. But essentially what we're trying to do is we have the field data, which is data coming in, and then we do the Syracuse assessment. And we all, like I mentioned, we have this, I should be pointing there, I'm pointing at my screen. So we have this instrument uncertainty, which is a fixed number. We have Syracuse here. And what we can do is from Syracuse, we can estimate a system uncertainty. So what is the uncertainty of the whole system? And the system uncertainty is contributed by two things. One is the field measurement uncertainty and the instrument uncertainty from, which is kind of inherent to the instrument. And then we can calculate this operational uncertainty. And ultimately what we can derive is a measurement uncertainty for each individual component. It's kind of the flow of this assessment. I'll show you an example of data from 3 measurement stations. One is our NREL station, 2 are NOAA's SURFRAT stations. These are very high quality stations. Everybody uses these for validation checks on other models. So we chose 2 of them. 1 minute data for 2021, 1 year of data. So here's the inherent uncertainty in the instrument. So this is the global instrument, plus minus 3.5%, the direct instrument, plus minus 2.3, and the diffuse is plus minus 3.5. This is NREL. SURFRAT has older instruments. The uncertainty is a little higher in the GHI. So this is what we get. If you look at it, this column is NREL data. This is Fort Peck, and this is Penn State. This is this whole thing. All these points. This is essentially the full system uncertainty. This is 1 year of data. These horizontal lines are essentially your instrument uncertainty, and it's pretty flat. One is for all 3 instruments together taken as a system, and the red is just the GHI. But nevertheless, what we do is we subtract out the uncertainty of the instruments to get the field uncertainty, and then use it to calculate the individual uncertainty in, say, 95% confidence, say for the GHI. You could do it for the DNI, you can do it for anything. But this, yeah.
What is it changing that it's changing the uncertainty?
Basically, what are these numbers?
Yeah, what
So
is it changing that it is changing?
it is basically the instrument response has an effect, because the instruments are not instantaneous. So if there's large fluctuations in the atmosphere, the instrument takes time to catch up. So that causes uncertainty. So then again, there is this uncertainty in it's more variability causes more uncertainty. So if it's a clear sky day, then generally the uncertainty is lower, because it's from one point to another, the uncertainty is pretty much flat. But the moment things change, the uncertainty grows, because the instrument actual radiation versus what you're measuring has a bigger band.
The response time of the
Instrument.
instrument is pretty high.
No, it's the measuring time of the instruments is, some of the instruments are 5 seconds. Some of the instruments are a little higher than 1 second, 3 seconds. So that has an effect. Basically, these are thermopile instruments. So you have to have enough photons. But
So what are is there a CCD? Is there a photomultiplier tube? What?
no, it's basically a thermopile. It's essentially it's a thermal energy to electrical energy.
And it's like it's a unidirectional. So you have some instrument and photons from every direction.
That's on the global. That's on the global. So you have this little detector, black detector, and essentially it absorbs all the photons, and then you have the it's what Seebeck effect. And then there is these devices which are very fast response. These are photovoltaic, photoelectric, but their problem is they have a spectral response. So that spectral response means that these are spectrally flat. So it can measure from, that's the reason to use it. You have to see from 300 to 4,000 nanometers. Yes. Yes. So that's why you use these instruments.
The reverse calibration can, use the CCD kind of thing.
You can, but again, the CCDs are only measuring in parts of the spectrum. It's not measuring the whole spectrum. So you have to make assumptions, don't you?
So that will add some uncertainty because CCDs are more sensitive to blue light than.
No, that is, if I have the response card,
You can do it.
Yeah, the response curve will add some uncertainty. So they have some other uncertainty.
Unless you can measure in that array from 300 to 3,000 or 4,000, the entire spectrum. Anyway, so here, this is a system in development. So we want to give this out so that anybody who does measurements can have an associated uncertainty. The interesting part is here. Again, these are three good quality, high quality instruments, but and this is the system uncertainty, the field uncertainty. This is an average over the whole year, and then there's the uncertainty in the GHI, which is in this case 3.58. This is more than 4%. Remember, I was saying 3% uncertainty. This is these numbers. Look at these numbers. This is 2.3% of the time. The uncertainty in the measurement exceeds the radiometric uncertainty. In these cases, it's 21%. So apparently, even good measurements can have significant differences in the quality of the data. Things we assume good, perfect, everybody uses it, they assume it's perfect, but this is what happens. So again, like I said, we don't not only measure solar radiation, there's all these other things we have to take care of so that a PV model can happen. I won't read through the list, but I'll just point out to a couple of things. You look at this circumsolar radiation, you have a 5-degree field of view. Normally in a radio transfer model, when you do direct, it's extinction, like it's a point, it's a pinpoint. So you can't measure it. So what happens is we have to build the models which can actually do circumsolar radiation, like that. Some of the scattered radiation, which is forward scattered, we have to ensure that the model contains that. Otherwise, you'll never be able to validate those models. So that's a challenge. Because more aerosols means more scattering around the sun. So you see a hazy sun. Good. Yes.
that's also beyond 5 degree.
No, but then that goes into the diffuse. That is counted as within the diffuse because ultimately the 5 degrees is a WMO standard for measuring direct radiation. There's aerosols. Aerosols are a big challenge. Soiling is big thing now. So UV irradiance, UV is also, we're working on UV, but we have built models which can convert global to UV. So all of this is necessary to ultimately do a good PV system work. So here's an example of albedo. Again, we're not putting these instruments on the back of panels to measure the radiation being reflected, scattered from the ground. But again, you put one here, in this point, it'll measure something. At the same instant, it'll measure something different here. How do you get an aggregate? These are practical questions, but very challenging. People are working on it. Hopefully, they will get to the. I personally, again, this is my aside, is that there is so little radiation coming back from the surface. We just assume some constant and get done with it. That's my take on things, but the industry thinks differently. Now let's look at solar resource modeling, because this is something I really love. Geostationary satellites, like I said, covered the whole globe. This is from NREL. I can provide you data which at any location. Again, geostationary satellites are 60 north to 60 south. We can't cover the poles. It's too oblique. So you have to use polar orbiters if you want something in Finland. But nevertheless, most of the solar work is being done here. Of course, there's work in Norway, and we are working on getting polar orbiters into the mix with NASA. So I have some collaboration with NASA, just trying to find a way to get all of that data in. But anyway, so this is what we cover. You can get this data from our website, and here's a model, simple, basically modeling sequence you follow to get to the solar radiation. Remember, again, at the end, we get GHI, DNI, and diffuse, GHI. There's this, on the top layer is the sources, the raw source of data. You have the GOES, it's just a geostationary satellite. In this case, GOES is the US satellite, could be replaced by anything. And MERA-2 is a NASA-based reanalysis data. You could check it out. Essentially, it takes observations, it takes models and produces a constant persistent time series of data, let's say 30-kilometer spatial and hourly temporal resolution. This data is a very good data set because it combines observations and models, and you can get 30 years of data. You could do lots of analysis with that data, trends, what is happening, different, basically, is a good monsoon or bad monsoon. You could, it's essentially a very good data set. So we extract, because solar radiation we're getting from the satellite, but some of the other variables we don't. So I get aerosol information from MERA-2 and also from MODIS, which is the polar orbiting satellite, which gives us aerosols. Combining the two, I get aerosols. And then the snow is an issue because snow is highly reflective, and also, so we need snow information because snow reflects sunlight and it again reflects back from the cloud. There's multiple scattering. So whenever there's snow, we need that information. Ultimately, what we do is we combine all this raw data into these things. The cloud properties, there's the atmospheric profile, there's aerosols, there's the surface albedo and the snow albedo. All of this gets put into a radiative transfer model. The FARMS is an inbuilt model. Again, we have to process 9 million pixels every timestamp. That's not trivial for the actual atmospheric model. The atmospheric models are much slower. This can do things in microseconds because what we did was we parameterized some of the transmittance. Works very well, and I'll show you that. But this is again just the same thing I talked about. It's a little bit more detailed. So if you see the presentation, you can understand this. There's a satellite input, the ancillary input, which goes into this processing system to get the cloud properties. These are the cloud properties we get. Then there is this ancillary data. All of it fits into this radiative transfer model. There's one model for clear sky, one model for cloudy sky, and then we also have models due to spectrals. It gives you the full spectrum. And then ultimately, here's all the products you could get. But nevertheless, that's what you can get from our website. It is just a sequence we follow to get to the final product. There's an example of the cloud product. So we can get cloud top temperature. What it essentially tells you is how high is your cloud. Is it an ice cloud or a water cloud? Ice cloud means that it's ice crystals. The scattering is not easy to calculate. Water drops are more spherical. You can get the phase function more easily. The symmetry parameter, single scattering albedo, all of that is much easier. For ice crystals, it's a little bit more tricky. So you have to work it out. You have the cloud top pressure and the cloud top temperature. So both of them together tell you what type of cloud it is. Then there's the cloud mask, which tells you whether it's essentially cloudy or not. This is a retrieval from all those satellite channels, which tells you is it cloudy or clear. Then you look at the cloud type. So essentially, we derive the type of cloud. It could be a cirrus cloud, a stratus cloud, different types of cloud can also detect some fog. Actually, what you have here is the measurement is the raw measurement is of course all the visible channels in the satellite, and then the infrared channels. Infrared brightness temperature kind of tells you how high the cloud is, and there are 1.6 micron and 0.64 micron. These are essentially tells you the phase of the cloud. There are at different heights. And also the other thing is that the 3x3 pixel variability tells us essentially is it a stratus cloud or is it a thunderstorm tower? Because in a 2-kilometer pixel, if there's one pixel has clouds and the neighboring ones don't, so we do a standard deviation, then we essentially say, okay, this is slightly different from the stratus cloud, which is covering the whole area, synoptic scale of the whole area. So no, it's both visible and infrared. It's the infrared is of course gives us a lot of information because the colder the temperature means the clouds are much higher. But the visible tells us gives us the optical depth of the cloud. That's a very important quantity. That's what we need to know. Two things. This one, the cloud optical depth, and the cloud effective radius. What is the size of your particles, and what is the optical depth? It means essentially the thickness of your clouds, because that drives your radiation. So all of this comes from the satellite. Reasonably complicated, but I think we've overused it.
The cloud temperature.
Yes.
That's like rings from.
It should essentially, I will say it should range from Yeah, it's there, but I'll tell you, it's like approximately, you should say 300 Kelvin to 200 and 30, minus 50 degrees centigrade to, to say 20, 30 degrees centigrade, full range, essentially. So, yes, it's cloud temperature, the top of the cloud. Yes, essentially. The very high clouds are very cold. They're all ice crystals, and they're probably at minus 40, minus 50, or even a little lower.
The density of the clouds.
This is what tells you the density, cloud optical depth. That's what essentially is the optical thickness of the cloud, which will ultimately goes into the calculation of how much attenuation of the beam will happen and how much scattering will happen in the cloud, the multiple scattering and all of it. This is the most important quantity. And then we know these other features, which is like the phase function. When it's ice, the phase function means essentially which direction will the photon scatter? Will it scatter upwards? Will it scatter downwards? In water, it's 85% forward scattering. In ice clouds, it's 90 plus. So essentially, if sunlight falls on an ice crystal, 5% will be reflected back and 95% will go downwards. In water, it's 85% will go downwards, 15% goes. So water clouds are more reflective. So all of this has to be, ultimately, we use all of this to in the radiative transfer model. So then, yeah, any other question? So now, essentially, this is our farms, which is the fast all sky model. Like I said, what we did was we ran this very high resolution, basically very high quality model, built a big database, essentially with multiple streams. So 16 streams, I think we use 16 stream die sort to build this big database for different clouds, different optical depth, different effective radius, different cloud type. And then we ended up building equations to fit, and I'll show you in the next sequence. And then we also, the clear sky is much easier, it's very fast. So the cloudy sky is where it take time. So we ended up, what we did was we ended up parameterizing the transmittance and the reflectance of these clouds. And that essentially made our function much faster. Because in actual radiative transfer in meteorology, they want heating rates at different layers. So they divide the atmosphere into 50 layers, and they will calculate at every layer going downwards. In our case, I care about what is at the surface. So I don't need to do all those calculations at every layer. I can just figure out effectively what 3 layers. One is like atmosphere above the cloud, and the atmosphere below the cloud. And that's about it. And I can make it into a much faster solution. So that's what we have done. That's why we can process 9 million pixels. It's highly accurate. We've compared it with the complex models. And here's an example. This is a 2-stream model, a real radiative transfer with multiple layers, and this is the farms. And so there's practically no difference in the accuracy. But speed, if you look at it, farms is this little thing here. This is farms. This is one, it takes 0.018 seconds to do one calculation. These are the others based on how many streams you use. And this is for doing a 10,000 calculations. Takes 2 seconds versus the next model is like the physical model is 12 minutes. So, of course, it's a no-brainer that we use this. We developed it ourselves. Anyway, so the NSRDB data is in all its glory. You can get time series. You can get all this cloud information I talked about. There's a thing called typical meteorological here, which is 1 year of data, which is kind of a median month stitched together to make a median year. There's UV, all of this is available. So I want you, if you have the presentation, you can get all of this, but you ultimately go to this website, nsrdb.nrel.gov. NSRDB is National Solar Radiation Database. You just go to their website and check it out. If this is if you find it interesting. And validation, again, if you look at the satellite data, here's the validation. We keep advancing our model regularly. So this is a comparison between version 3 and version 4. Let me tell you one thing. These are stations, ground stations, high quality ground stations of known accuracy. And this is the evaluation of, this is the mean bias error for these stations when you compare with our satellite data. And these are 2 versions of the model. The latest is version 4, and version 3 was just the previous version. This is for GHI. So we are within plus minus 5% of the ground measurements wherever we compare. So it's pretty accurate, our satellite products. This is the DNI. DNI is, of course, a little higher accuracy is a little lower, or main reason being that satellite sees 2 kilometers and a ground measurement is a point at the ground. It's apples and oranges a little bit, so there's more uncertainty there. But then nevertheless, what I can say is the satellite data is pretty good. You could use it, it's available. Oh, the y-axis is just percentage. So that's why I said this is plus minus 5%. This bar. This is the bias, there's the mean absolute error, and then the RMSE. All three are there. So I just pointed out, in the interest of time, I pointed this out to you. But any of you are free to email me if you find, if you're interested in getting more information about it. Then again, there is, like I mentioned, in the solar modeling side, there's a worldwide benchmark. So there are all these different models. So we, as IEA, we have a work group, and then there's this report which benchmarks different, like I have my NSRDB, there are other free products and there are some commercial products. We participated in this comparison. They got good ground data around the globe and then did an evaluation. It's very interesting read if you are interested in how good satellites can be in assessing, in measuring solar radiation or modeling solar radiation. Anyway, so there are all these downstream models too, and I won't go into the details. There's ultimately, remember I mentioned you have to do things at a tilt. So there's all these models are available in a public repository, so you can get this. Finally, I'll just mention this quickly in passing. We're running out of time. There's forecasting, and forecasting requires different technologies. If you look at the horizontal axis, it goes in seconds to minutes to hours to days. And then the spatial resolution can be very low to very high. And you could use a sky camera to do very short-term forecasting. You can do it with a satellite, like cloud motion vectors, how the clouds move around. These are very challenging questions, but these are things people are doing. And then there's a weather prediction model, which don't do very well, so we're trying to improve it, doing probabilistic forecasting, ensemble forecasting, essentially to essentially give you a forecast with a band of accuracy, and the band keeps going up and down depending on atmospheric conditions. Again, the sky imager forecasting is, I mentioned, there's been a comparison. The main thing is they're also doing machine learning approaches using sky imagers. Problem is that they're smoothing out things a little bit too much. So the physics and the machine learning have to be combined. That's our current thought, ultimately to end up with a better forecast. Like a satellite-based forecasting is ultimately we take multiple images, we track to see which direction the clouds are moving, and calculate this cloud motion vector, and then we project the clouds forward. Here's just an example cartoon of a model we developed. This is Puerto Rico, and as you can see, that the clouds, these are real clouds which are moving around. It's a forecast we produced. So this is just an example cartoon of what these. The blues are those clouds essentially, and this is basically where the cloud is throwing a shadow. This is GHI. This is the forecast of GHI. So wherever it is blue means low GHI, which means that there's a cloud there, essentially. So this is, oh, I forgot to put the color scale on, sorry. But this is what happens in, we had in San Juan, in the city, this. Okay, the blue is the center of the cloud, and the white is basically essentially what these are. So they're merging, kind of. Some of those clouds are breaking apart. Some of them are merging because this is a tropical environment where you have these thunderstorms popping up. So it's a very unstable environment. So that's what. Again, some of these might be noise too, but because we're trying to work this out, this is work in progress. It's like a very complicated thing. Imagine like you have this cloud, you're at every pixel and you're trying to group it together, and you have these wind speeds you're deriving, and wind speeds are not constant in one direction. You can see it. Different cloud is lower level is moving in one direction, clouds at a higher level moving in another direction. And you're trying to forecast all of it. So there's probably uncertainties here, but at the end of the day, this need to make more advancement. That's all I can say. But people are working on this, and it's an essential part of the forecasting suite. Then I just mentioned the NWP-based forecasting. So you can look at WRF model, which is essentially freely available. If you want to run a weather model on your computer, go download the WRF model and you could run it. What we are doing is probabilistic. So we understand that forecasts are never perfect. So might as well give people a sense of uncertainty so that when somebody is planning solar plant operation tomorrow, they know that I have a forecast, but it's going to be 100% uncertain. So you better be careful, have enough reserves so you don't shut down your grid. These were some comparisons, benchmark comparisons we're all conducting on solar forecasting. Essentially, this thing called CRPS. The moment you have ensemble forecast, you can't use the deterministic thing. So we use the CRPS, which is essentially RMSE for probabilistic data. But this is work in progress. Probably report on some time. But anyway, the climate impacts this is what I'll say. If you look at this plot, but you should study this. This is part of the IPCC report. Many of you have seen it. It's the radiative balance of the planet. What comes in, what goes out. What we're finding, and this is for solar applications, and it's very troubling, is if you look at this plot, this is observation. And this is what the climate model is showing. Same thing, this is a bias when you compare with 25 years of satellite data. We're correcting it, but this is only on the solar radiation side. So we have to talk to the climate modelers to see what's going on. They're under-predicting clouds, which is a serious challenge. But again, we're looking at solar applications and we are looking at it with a microscope and then trying to fix things. Here's a good resource. I will point it out. It's published at NREL. It's all free. If you don't do anything, just download a copy of this PDF and look at the chapters. It will give you practically everything about the solar radiation and how it gets applied. It's just free, just download it and have a look. It's got all the references, and it's by 40 authors from 14 countries. All the experts in the world got together to write this. New editions coming next year. So here's the IEA task I was mentioning. Finally, there's also the system advisor model. If you want to go the next step and produce your own solar, design your own solar field and see, here's my panel with this orientation, this technology that is very easy to use, very handy, just as a curiosity, but this is something which industry uses. So it's all free and from NREL, so if you want to use it, test it out. It could be a nice student project, but not in, of course, your astrophysics. It's who could be interested in this? So these are free resources, very easy to use. They could design something and see what's happening. So some final thoughts, of course, measurement and modeling of solar radiation has improved over the years, but still work to do. Probabilistic solar forecasting, it's part of the mix now, and then the advances in solar forecasting at all scales is still work in progress. Finally, we need to reconcile the climate biases, especially for solar energy. And thank you. I did run out of time. Sorry.
Okay, thank you, Dr. Sengupta, for this very informative talk. Yes, there is a mic.
It is on there. That's what it is.
When you were talking about those, I mean, cloud reflecting versus and cloud transmitting storm. So can you just go back to that slide?
Yes.
I'm just confused about the color. So what does that color bar signify?
Oh, these the transmitter is these different colors. In that it's essentially the solar zenith angle. So you have a cloud, and if your sun's at a high angle, then the path through the cloud is much longer. So that, and then it's like cosine of the zenith angle. So if you look at it, it goes from 0 to 1. So essentially there are a lot of curves in there, and these curves represent the angle of the sun. That's what is represented. Mu zero, and oh, this is the DE is for the effective the effective diameter of the particle, basically. So mu zero is the angle of the sun, and DE is the effective size of the particle.
Other questions?
Thanks for the nice talk. So I just had a basic question. That is, so basically you compared the farms model with some other like 2-stream, 4-stream and also I was confused regarding what are those 2-stream, 4-stream, what are those models basically? That wasn't very clear.
Oh, what is the two? You can have, these are, so essentially you can divide your hemisphere into multiple angles, which are to calculate your radiances, not to, and ultimately integrate it to get your irradiance. So the more streams you have, essentially it takes longer, but you're essentially getting information from calculations from multiple streams in the hemisphere. Yes, you're increasing resolution in the solid angles are smaller, you're increasing resolution. So higher 64 streams probably gives you much more.
Next slide.
Yes,
That's so we went up to 16 streams, but beyond 16 streams, the accuracy is for especially the clouds we are modeling, the accuracy doesn't change by much, but so you could add 32 streams. It goes multiple 32, 64, 128, but it essentially, you look at the time required, it goes from 31 minutes to like 3 hours.
Thank you.
Other question?
Yeah, so that lovely GIF that you had shown of CHI predictions that are moving over the co-curricular.
Yes.
So I wanted to see that what was the time scale of the prediction.
Oh, yes. It's supposed to be 3 hours, but I'm not sure.
3 hours.
It's a 3 hour.
Okay, so it's happening over a 3 hour.
Yes, so
Right. So 5 minutes is good. So what I was concerned about is, or what I wanted to know is that since we are talking about variability at the scale of 5 minutes, so isn't the battery or storage capacity enough, or the storage technology enough to balance out the variability caused due to?
yes.
So because if it's a very long scale thing, then the battery storage technology becomes a problem. But if it's 5 minute variability or even 3 hour variability, is the
Battery is not an issue at the 5 minute scale. So battery is never an issue at a very short time scale. What this variability is mostly when you don't have batteries and your whole region essentially has the generation is fluctuating. And then what you're trying to do is it's peak hours, you have to pull up some of your reserve to essentially balance the grid. So that's when this comes into effect. But the variability is when you have, see right now 10% of the grid supply is probably from solar. Now imagine 50% is coming from solar, then how much variability will you encounter? And then you have to, your batteries can supply it, but you can only have that much battery. So sometimes you might have to curtail the thing. Like you curtail some systems and say these systems are too variable. I will not accept delivery from the grid. I don't know these solutions. The electrical engineers come up with some magic sometimes. They and solve some of these problems much more easily than I can imagine. But this is what they're looking for. So tell me how variable this whole system is so that I can build technologies around it.
So my question is, in this slide, you mentioned that 3 hour focus for every 10 minutes. So is this data publicly available?
So no, we don't. This is not done operationally by us. I'll tell you the main reason. This is demonstration we did, but we don't produce it operationally because there's private companies who sell these forecasts. So we can do demonstrations. We are not allowed to compete as research institution. We can't put free stuff out and compete with the industry and kill them. So, but the data from the satellite, so you could, if you want to build something like this, you have the NSRDB, I told you. So you can take that NSRDB data, which has all the information at 5 minutes, and you could essentially derive this forecast in hindcast mode. Basically, okay, you build your technology, but data is available. So you build the forecast. The advantage is you can also validate after, because you have 1 year of data. You build your thing, and then you have the next 3 hours of data available to check to see if it's working or not.
Because I'm asking because it will be helpful for sky observing, right? If we get this data for the next 3 hours, it will be helpful for us sky observing.
Yes, I understand.
Telescopes.
Yes, I understand. At the
Observe
observatory.
sky. Yeah.
At observatories, basically.
But, this kind of, I mean, for NOAA website, the next 6 hours, how the clouds will move, that is already available, right? It's not like that.
There is some forecast available, yes.
Yeah, because whenever do observation.
Those
they
are
always
general,
look
yeah.
At these websites and make sure that tonight the sky.
They
will
do.
be-
This is just looking for more
This
accuracy.
is much more accurate, that is the thing. But spatial resolution wise, time wise, it's much more accurate.
Yes.
But broad information, broad information.
Yes, all Nova's of GFS, you look at GFS, it's publicly available.
Because if you know this from, I mean, if you go to where from where.
Oh, yes.
For the next 12 hours, it's there. It may not be very accurate, even for a week, but that is a predict. Yes. So the accuracy will be less, resolution will be worse, time and spatial. Here you will know that, okay, Kolkata will be fine, Salt Lake will not be there, it may be just, the entire area. It's like.
Okay.
Other questions? Okay, Manajit.
That's a very nice talk, and I'm really happy to see that machine learning and physics are connected.
Oh, yeah.
I have a very off-topic question that for weather prediction, which type of machine learning models are you were using? What are the features that you were feeding the network?
So again, this is for that short term. They're basically it's mostly neural nets. That's what's being used. Yes. So and what gets fed into those it could be people do the red blue ratio in CCD based those cameras to identify clouds, and then they put multiple sequence of images, and that's how they try to track it. So that's what they're doing in that. So it's again, machine learning is getting used at all levels. We just have to be a little careful that what it is getting us. I personally am I'm always very careful. The other thing is that I see a lot of papers coming in. I'm an associate in Solar Energy Journal. People are using this machine learning. Here's my forecast. I said, so what? It's just like a tool you used and you produced a forecast. So how did you advance the science? You have to first explain that somehow you advance the science and somehow explain why you got your results. Using a black box and getting improvements though is incredibly hard. It's not that easy. I will tell you, our physics is not, it's well formed. It's so sometimes it's very hard to beat the physics. And then some people are reinventing the wheel. Maybe just take some data, and we already have the equations for that, and then they take some data and reproduce the equations using machine learning. I see all sorts of funny things happen. So you just have to be careful. It's a good buzzword. We'll probably get you funding, but we have to be careful how you use it.
Other question?
Okay, so I was wondering that cloud modeling and so loud. So it's cloud modeling and talking about like weather modeling. So turbulence must be playing a big role here.
Turbulence plays a role at the lower atmosphere, especially important for wind. And then, yes, you have vertical mixing, and when you have unstable, lot of heating, then definitely the parcels rise much faster and then they form these thunderstorm clouds. Yes.
So is that included in this kind of modeling, like the turbulence?
It ultimately, in the weather models, absolutely. The weather models, are planetary boundary layer models are extremely complex. Those, if you use the weather research and forecasting model from NCAR, this is from National Center for Atmospheric Research. If you go there, you could download that model and you could just essentially, as student projects, you could essentially use this and use the GFS. Again, that's free data, the global forecast. You need a boundary and initialization, initial conditions. So you could get WRF and you could try to produce a forecast of say West Bengal. So you can get the GFS as input. GFS is also free, or there's other data sets which are free, and people could just run off their own little forecast. And what happens is you could choose different parameterizations. There's a whole suite. So boundary layer parameterizations, you can compare what works, what doesn't work.
Second one is like, it's not a question, it's just an information. So this kind of work, like equivalent to what people are doing at India, is there like an equivalent where this kind of work goes on?
For solar energy, unfortunately, no.
Okay,
That's the answer.
I have tried a lot. I wanted to provide the satellite models to somebody in India so that we don't have to occasionally, because I don't have funding on a regular basis to produce satellite data for India. I said that I'll give you the codes, I will help you, handhold you, so you produce a data set which Indian developers can use. I have asked the ministry, I have asked National Institute of Solar Energy. Nobody's going to take it up. Meteorology department will not take it up because it's solar energy. It's like nobody's essentially. I have offered all the help, but because then what happens is India gets a data which is updated even daily. But again, we just need, and you don't have to do basic research. I'll give you everything.
Other question?
So, from the raw satellite views, while you are measuring
Like ground temperatures and optical rays, etc. The future shows that it involves a lot of modeling.
Yes, there are these models.
How does one validate those models?
Using ground measurement for solar radiation and the radiation models, there are these programs. If you have heard of the ARM program, it's called Atmospheric Radiation Measurement Program run by DOE. And they have measurements with radar. Yes, if arm.gov, just go to arm.gov and there is this program, and this is global data is available, like a lot of other intensive observational data sets were available from multiple locations, but there's one permanent location in the southern Great Plains in Oklahoma. And they have radars, they have LiDARs, they have, you name it, you can get like these micropulse LiDARs where cloud base, you can look into using these cloud radars, you're looking at each of these layers to see whether ice or water, and at 45-meter resolution, you can get all these data to essentially validate this. It's a very that program has spent a lot of money to just build this so we can use that data, and it's available to anyone.
Other question? I had a couple of questions. One is a very broad question, which is, let's say a lot of solar panels are deployed all over the earth. Will that change the Earth's albedo significantly?
No, the Earth is so much bigger. Our assessment was if you have 100 miles by 100 miles the solar deployment in the Sahara Desert, it can supply the whole world. So that is the magnitude we are talking about.
Okay. And can you go back to where you first showed the model? So you showed a map of the entire world, the irradiation map. And the next slide was something about modeling. Yeah, this one.
This one.
So by the way, so going back to that map, you don't have data for the ocean?
We do, we don't process it.
Okay.
Because nobody's built till now nobody's building solar plants on the ocean. So we just wanted to reduce our computational burden. But right now, I was just told that we are trying to build some near shore water body, calling it floating PV or photovoltaics. So now my task is cut out to provide some data. I doubt they will be able to deploy in the ocean, on lakes maybe, because lakes are calm. Um, uh,
So
ocean-
what, I mean, again, there are so many things. So for example, in Africa, there is a yellow patch between two red patches. What is the reason for?
That's lower solar radiation. It's basically, if you look at weather patterns, there's more cloudiness there.
More cloudy. Yeah, but it's still more cloudy. So this is the average over a year, right? So this is sort of an average over a year.
This is, yeah, this is the average over a year,
Or
yes.
more than a year.
Yeah.
Yeah. Equator. So southern hemisphere, all the continents are, all the countries are very closer to the equator than the northern.
Yes.
Australia is almost equator side. Is it influenced by the tilt of the earth?
Which one? See, northern latitudes will have, of course, lower total solar radiation. So if you have two places with zero clouds, let's assume, but if it's a little higher up north, naturally your
Higher
sun
latitudes get
less, overall less, and you can see the trend.
That's just the seasonal.
Yeah, and then India has its own problem because India has too much aerosols. You can, so definitely that impacts your solar radiation. So cleaner atmospheres. Atacama Desert has the world's highest solar resource. Yes, Chile. It has the world's highest solar resource. Our has good resource. Again, the Southwest US has very good resource because it's not only is it desert, it's clear, but the aerosol loading is also low. So that matters.
We don't have Hawaii yet.
It is there. It is in Hawaii. We do have data for Hawaii, but it's probably not showing up.
So, go back to that slide where you have the models. So there are these 4 satellites that you have.
Satellite are sources of
listed
data. I
here.
will say sources of data.
But then, is it, I mean, for the GOES satellite, you can still apply all these atmospheric profile, aerosol profile, properties, etc. Or no?
Yes. Yes.
So, I mean.
you can
GOES
replace GOES with Himawari, say, which covers Australia and Japan. But MERA 2 is global. MODIS is global because it's a polar orbiting satellite. No, we use the GOES data to produce the cloud properties. Yes. MERA 2 we are using because it provides us hourly aerosols, essentially from combining models and the polar orbiter. And MODIS is additional augmentation of the aerosol data information. IMS is just like a microwave satellites combined together. It's a product, but it's northern hemisphere. It doesn't do.
So all this information together goes into farms and that produces.
Yes. So yeah, it's the overall scheme is pretty clear. It's more of like the individual details, sometimes little bits, and the accuracy will change based on how good my aerosol is. Dust storms in Middle East. How well can we capture it? How well does MODIS capture it? Those are questions basically sometimes as we put more solar farms in difficult locations.
Okay.
But it's interesting if anybody, the main point is that this is an area where you can contribute as physicists. If you get interested, you can go get a PhD in atmospheric science. That's for your master students. If you think this is an area you want to explore, please do. So that's my main point.
There are models.
Yes. Main aerosols, it's all we are driving everywhere, we are burning fuels, we are using machinery, a fossil fuel, and also you look at what is happening in New Delhi.
Burning of agricultural products.
So I will tell you as anecdotally, the aerosols are 5 to 10% higher on average than say the US, which is extremely high. So, but again, it's because of we're churning up dirt, we are pumping more aerosols, and then there is pollution stacks, which are, of course, huge sources.
Okay, so if
Anyway.
there is another question, let's thank our speaker again.
Thank you, everyone. Thanks for hanging around till 5 o'clock.
Yeah.
It was meeting after a long time.
So there is
Yeah.
a fee here. It was already told you.